Hey guys. Alright, so we are going to do a problem that deals with this is applied forces at angles. So it's a different type of problem, and the best way to show it is through example. There's really two different ways I could ask this question, and while I'm only showing one, I will discuss what happens in the other way as we go through the problem. So, the key thing is the difference between the drawing of the picture to understand what's going on and the free body diagram in these problems. So, first of all, just draw the picture. We have a 70 kilogram lawnmower. We don't have to actually draw the lawnmower, but 70 kilograms being pushed, so it's going to be on the ground. The lawnmower is going to be on the ground, obviously. Going to be pushed with a force 900 newtons at 40 degrees. This is a new way to classify an angle, below the horizontal. So, lawnmower is going to have that handle. It's a push lawnmower. And the force is going to be pushed down the handle. So we know it's 900 is the hypotenuse. So when it says below the horizontal, kind of just like we had like east of west, or east of north, or whatever the case is, the second one was the one that mattered. Well, the horizontal is this. So horizontal says we're not horizontal, we're below it, so below is kind of like south. So our angle is that angle. So as drawn, like this part would be, switch to red, this part would be our 40 degrees. And I'll redraw this in a second so you can see it. But this angle right here, it would be 40 degrees. So rather than saying south of east, we would say, in this case, below the horizontal. You could do the same thing. Below the horizontal would also be that angle. It's not really a very descriptive way of giving a true direction, but usually we just assume the motion is to the right. It kind of just makes things easier because to the right is positive. So both of these would be BH, or below the horizontal. The other way to ask this would be AH, or above the horizontal. So those are BH's. AH would be an angle like that, or an angle like that. Both of those would be considered AH. So this case we're dealing with BH, but in the worksheet you'll have AH, and again, as we're going through this problem, I will discuss how that will change your values. So let me clear and redraw. So we've got our lawnmower, 70 kilograms on the ground, getting pushed. Here's our angle with 900 newtons, 40 degrees. So, well, let's just look at the forces. That force is being applied sort of at this angle. You've got the force of gravity. There is friction. It says coefficients of friction. So friction is always going to act opposite of the actual direction of motion. And we all know that a lawnmower is not going to go into the ground. It's not going to like somehow go that way, because the ground's going to stop it. So the actual motion is going to be that way. That's the direction of motion. Again, this is not a free body diagram that I'm drawing. It is just a picture representing what's going on. So the direction of motion is that way, which means that my force of friction, whether static or kinetic, is going to be back to the left as I'm drawing it. If you drew it other way, it'd be back to the right. Whatever the opposite direction of motion is. So we are figuring out what's happening to the lawnmower. So since there's static, we got to see if we're pushing hard enough to break static friction. If it is accelerating, so if we are pushing hard enough to break it, we've got to find the value of the acceleration. So how do we do this? This is where free body diagrams really do help. So first of all, this force, the 900 newtons, 40 degrees below the horizontal, we break it apart into its pieces. This is an applied force, so you've got an FAH, horizontal applied force, and you have an FAV, a vertical applied force. Remember, with subscripts we read them backwards. Horizontal applied force, vertical applied force. So the vertical applied force in this case is going to be FA sine of the angle, so in this case 900 sine 40, and the FA horizontal is going to be FA cosine of the angle, FA cosine of the angle, so 900 cosine 40. 900 cosine 40, my calculator, is 689.44. 689.44 newtons. And that's going to be acting to the right. And my FAV is 900 sine 40. And it's 578.51. 578.51 newtons. And that's going to be acting down. So, original free body diagram, I would have had FG, then I would have had FN, I would have had FF, and I would have had my FA, where the FA is 40 degrees. But that's not a good free body diagram because we don't like the arrow with the angle. So I'm going to use my broken down pieces to redraw my free body diagram to simplify it like we had been doing. Got the normal force, force of friction, that's all set. It's in the correct coordinate axis. Got my force of gravity. But my applied force, I don't want to deal with the angle. So I already broke it apart. One force, my FAH, is to the right, and my other applied force piece, coming from the center of the Cheez-It, is FAV. Plugging in numbers, we've got to be careful of certain things. So FAH we know is 689.44. You know our FAV, 578.51. The only thing that would change in terms of if this were an above the horizontal or below, the FAV would have been upwards instead of downwards. That's the only thing that would have changed, and it'll change another thing in a second, but I will explain as we go. Our FG is the mass times 9.8. That hasn't changed. So 70 times 9.8, 686. 686 newtons. Our force of friction depends on our normal force. But we have to be careful. Our normal force, usually we just say, oh, it's 686. But with these problems, the normal force, you have to look at our F net Y. And we did that in the equilibrium problem, equilibrium lab, I should say. Our F net Y has to be 0. The lawnmower is not going to go into the ground. It's not going to lift off the ground. So we have 3 vertical forces. We have our normal force, which is up, that's our positive direction, minus our 686 from gravity, our FG, minus, this is FAV, down, so minus 578, I'm going to run out of room, 0.51, 578.51, that is our FAV. The only reason I changed colors is just because of my background. If this were above the horizontal, the only thing that changes is my FAV is up. So this becomes a positive instead of a negative. So below the horizontal, this is a negative number. Above the horizontal, this is a positive number because this FAV is up. So I have to solve this equation for normal force. Well, normal force is going to be, solving all that out, my normal force is 686, or negative 686, minus 578.51. So my normal force is 1264.51 newtons. Remember, the ground pushes exactly what it has to. If I push harder on the ground, the scale reads more, the apparent weight seems more. So my normal force is 1264.51. I push into the ground, so like with friction, those hills and valleys of the top part and the hills and valleys of the bottom part stick together a little bit deeper, and we have more friction because friction deals with the normal force. This is the reason we deal with friction as normal force, not force of gravity, because gravity hasn't changed. But the normal force we can manipulate depending on how we pull up or push down in this problem onto the surface. We're pushing harder down, so the ground has to push harder back up to stop the lawnmower from going into the ground. So then our force of friction, depending on what we're looking at, we got to see if we're pushing hard enough. So we've got to look for our FFS max. And our FFS max is going to be our static friction coefficient, mu s times the normal force. So 0.4 times 1264.51. 0.4 times 1264 is 505.804, so 0.80 newtons. So we are pushing hard enough to beat our static friction. So we're making this thing move. So what is happening to the lawnmower? It's moving. Moving because FAH, the only part that we care about to make the lawnmower move across the lawn is our FAH. So it's not the whole FA, it's not 900 that we look at. We already got rid of that one because FAH is greater than FFS max. So now we got to look to see what the acceleration is. Our acceleration comes from our net force. But with our acceleration, since it's moving, we've got to use FFK. And I think it's time to redraw this. So we had we already took care of those. FG, FAV, FN, those, the same numbers, you would put those back in. I just ran out of space. So our FAH was 900 cosine 40, so 689.44, 44 newtons. We've got to figure out what our force of kinetic friction is to find our net force, because we have to find that net force, mass times acceleration, is FAH plus our FFK. We're going to have a negative here because they're in opposite directions, to find our ultimate acceleration. So FFK, because we're moving, that's why we have to use FFK, is 0.2 times the normal force, 0.2 being the mu k. So 0.2 times 1264.51 is going to give us an FFK acting backwards of 252.9. 252.90 newtons. So this number back friction is 252.9 newtons, and again you would have numbers for each of these that you should label on your free body diagram. So now we're ready to find the acceleration. Our mass was 70 times the acceleration. FAH positive 689.44 minus FFK opposite direction in the negative direction minus 252.9, 252.90. Solving for acceleration is 689.44 minus 252.9, 436.54, 436.54 divided by 70. So I kind of did two steps in one. First subtracted those two, that's 436, then divided by 70 to get an acceleration of 6.24 meters per second squared. As I drew it, we're going more right, so I would say to the right because we need that direction. So find the acceleration. We made a free body diagram dealing with kinetic friction. Again, the only thing that would have changed if it were above the horizontal is our normal force would have been less, so our forces of friction would have been less that we had to deal with. So we would have gotten actually a lot higher acceleration, and you'll try that with some of the problems. All right, if there's any questions as you're going through this, by all means, call me over and I'll try to explain. All right, good job.